sequences. We're going to kick it off with an investigation that I'm going to allow you to do mostly on your own because it's really familiar stuff with regard to ratios and exponential functions and things like that. But what we do have is a radioactive substance, often used by doctors for diagnostic purposes because they can be injected into the bloodstream and then it can be viewed using a special camera. So here we have thallium-201, short to TL-201. It is a radioactive substance and a patient is injected with 50 MBQs of it, which is a becquerel or a microbecquerel. No, megabecquerel. So 50 megabecquerels. They're injected with it before undergoing a procedure to take an image of the patient's heart. The half-life of thallium-201 is 73 hours. So we're going to copy and complete the table there. You're going to write the amount of thallium-201 remaining in the body as a sequence, with 50 being the first term. So you'll have 50, then 25, then 12.5, etc. And then talk about that sequence. Is it arithmetic? That's the sequences you learned about yesterday where there's a common difference. You'll know the answer to that once you complete the first differences column. You're going to talk about that pattern, and then you're going to, in step 5, divide each term by the previous term and see what you notice there. So you're going to identify that this is a geometric sequence and that the relationship between each term is that there's a common ratio. Go ahead and take on that investigation, pause the video, and pick it up again for some notes on the top of the next page. In step 6 of the investigation, it says to write each term as an expression involving the original amount, A, and develop a formula for the general term. So the general term is T sub n, and basically what you're figuring out is that you have the original amount, we're talking about half-life periods, and n is going to be the number of periods, number of 73-hour periods. So to get a specific general equation for this situation, our initial value is 50. We're talking about half-life, and we're going to cut it in half every 73 hours, which is one time half-life period. Okay, so in number 6, this should be your final answer. If you got that on your own, way to go. You're well on your way. Let's take some notes on the top of 17. The first note that we're taking is geometric sequence. Okay, geometric sequence. This is a sequence where the ratio of consecutive terms, geometric sequence, a sequence where the ratio of consecutive terms is a constant. That means that to get from term to term, you are multiplying by a constant, okay? Subnote. The terms of a geometric sequence, are found by multiplying the terms of a geometric sequence are found by multiplying the first term, which is A, and each subsequent term. So all the next terms also work this way, and each subsequent term by a common ratio. Okay, that's our constant that we're talking about. So let's take a little note just on common ratio. Common ratio, this is the ratio of any two consecutive terms, the ratio of any two consecutive terms in a geometric sequence. So kind of the same relationship that we had between our terms yesterday. If it has a common ratio, it's a geometric sequence. If it's a geometric sequence, there's a common ratio. If not one, then not the other. Okay? Here we go. A geometric sequence can be written, geometric sequence can be written A, AR, AR squared, AR cubed, dot, dot, dot. Okay, so you can see what's happening. You take the first term, multiply it by your common ratio, multiply that term by your common ratio, multiply that term by your common ratio, and all you're really doing is repeating the factor r, which is same thing that we have in that we're familiar with exponential equations. Okay. Last line, the formula for the general term is T sub n equals a times r to the power of n minus 1. So the term number, there is one less factor of r than the term number. Say it again. Term 1, no factors of r. Term 2, 1 factor. Term 3, 2 factors. Term 4, 3 factors, and so on. Little qualifying rule here, where r cannot equal 0 and n belongs to the set of natural numbers. Well, let's take these definitions and apply the skills that we really already have working with exponential functions and dive into some examples here. In example 1, we're asked to determine whether each sequence is arithmetic, geometric, or neither, and then justify our answer. The first thing I'm going to check for is arithmetic. In my head, I can do it real easy. 5 take away 2 is 3. 10 take away 5 is 5. No common difference. But I'm going to just write it out so that we know what we're doing. So here we're going to check for arithmetic. 5 take away 2, 3. The difference between consecutive terms, right? That's what we're talking about here. Term 3 minus term 2 is 5. No consecutive, no common difference. Therefore, not arithmetic. So, check for geometric. Now, if you were doing this in your practice problems, I would definitely not expect you to write this each time. But to check for arithmetic, we are looking for a common ratio. So what we need to do is take term 2 and divide it by term 1, the preceding term. 5 over 2 reduces to 2.5. And we'll do the same thing. We'll take term 3 and we'll divide it by term 2. 10 over 5 divides into 2. No common ratio. Therefore, not geometric. Okay? This guy is neither. Example B. We have the sequence 0.2, 0.02, 0.002, 0.0002, and it's going to carry on. Oh, they sure made this one easy on us. Um, is it arithmetic? Well, definitely not. So I'm not even going to bother checking that. Also, I can already see that it's geometric. I'm going to be multiplying by 1/10. Okay, so here we go. For geometric, we're going to check for a common ratio. I'm simply going to take the second term, divide it by the first term, see what I get. And I'm going to take the third term, divide it by the second term, see what I get. And just to make sure, I'm going to take the fourth term that they give us, divide it by the third term. Be careful with your zeros and see what we get. And if we get the same, if it reduces to the same number, then we have a common ratio and it'll be geometric. Well, you can do this in your head or in your calculator. Doesn't matter how you do it. You're going to get 1/10, 1/10, 1/10. There is a common ratio. Therefore, geometric. All right. C. In C, we are given the sequence a plus 2, a plus 4, a plus 6, a plus 8, so on. Again, it's pretty straightforward to see just directly here, but I'm going to go through the steps anyway. I'm going to check for arithmetic just by looking at it. I think it is arithmetic, so I'm going to check. We've got a plus 4. That's our second term, and I'm going to subtract our first term. Okay? I'm going to figure out what that is. Then I'm going to take our third term, which is a plus 6. I'm using brackets so that I know that I'm going to be distributing this negative sign to both terms in the binomial. And I'm going to work vertically for each of them to see what I get. And we'll do one more just to make sure. A plus 8 minus a plus 6. All right, here we go. A plus 4, and this negative is going to distribute to both terms in the binomial. This whole term is getting subtracted, so I've got minus a minus 2. A minus a is 0. 4 minus 2 is 2. Here we have a plus 6 minus a minus 4. A minus a is 0. 6 minus 4 is 2. And here we have a plus 8 minus a minus 6. And that's 2. All right. So here we have there is a common difference. Therefore, arithmetic. All right. So that kind of example gives you practice using the rule that you have for an arithmetic sequence and a geometric sequence and testing things out. In example 2, we are asked to write the first 3 terms of each geometric sequence. That's as easy as plugging in n equals 1, then n equals 2, then n equals 3, and calculating it out. So here we go. For example 1, we're going to do the first term, the value of the first term, simply going to plug in 1 for n. I'm going to just go ahead and write each little piece that I'm going to do. I'm going to find the second term, in which case I'm going to plug in the 2 wherever I see the n. And for the third term, you guessed it, I'm going to plug in a 3 wherever I see an n. Okay, back to term number 1. Bed mass. So we've got an exponent here to deal with. This is 3 to the power of 0. That's 1. 5 times 1 is 5. The value of the first term is 5. Over here we've got 3 to the power of 1. That's 3 times 5, 15. Here we have 3 to the power of 2. That's 9 times 5 is 45. And if you're going to double check your answers on things like that, you can see it's geometric, which we were told. So to get from one term to the next, there should be a geometric pattern. That is, there should be a common ratio, a common multiple, really, right here. 5 times 3 is this, times 3 is that. The next one will be times 3 again, and you could carry on down the line, okay? Just going to clear that off. B, the function that we are given, the equation for the general term is t sub n equals 16 times 1/4 to the power of n minus 1. And take note again, it's always the general term and to the power of n minus 1. Okay, so here we go. We have to find the first term, and I'll use the same notation. Just plug a 1 in where you see an n, and really all that does is give you r to the power of 0, which means no r, right? And we talked about that already because t sub 1 is the same as a. The first term is a, which is in this case just 16, because this whole piece becomes 1. And anything times 1 is itself, okay? But let's work this down. We've got 16 times 1, which is 16. Second term, 16 times 1/4 to the power of 2 minus 1. And I'm just going to write out my equation for the third term. 16 times 1/4 to the power of 3 minus 1. Going back to the second term, 1/4 to the power of 1 is 1/4. 16 divided by 4, or 16 times 1/4 is 16 divided by 4. That's going to be 4. In our next one, we've got 1/4 to the power of 2. That's going to be 1/16. 16 times 1/16 is 1. And again, you can see jumping from the first term to the second term to the third term. Each time we're multiplying by, you guessed it, our common ratio, 1/4. Okay? Nothing too terribly surprising there. Let's go for our last one. In example C, we are given the first term, a, which equals 125, and we are given the common ratio, r, which equals -2. All right, so here we could use the general, you could do it two ways. You could do it first by using the general term, or you can just use some inference here. A is the first term, so the first term is 125. And then how do I get from the first term to the second term? Well, I simply multiply by -2. So this is going to be, I'm just going to write it -250. Term 3 is going to be, again, take term 2, multiply by -2. You're going to have 500. Now, I didn't use the explicit formula to do that. I kind of dealt with it as a recursion formula, but it's all good. Just so I don't leave you in the dark, I could have used the general formula here, a r n minus 1, in which case for the first term, or let's just do the third term, I'd have the third term with an a was given, 125, times r, which was given, -2, to the power of n minus 1. And then followed that down, and you guessed it, I'd get 500. Okay? In example 3, we're asked to determine the number of terms in a given sequence. So we're given the initial value, 4. We can figure out the common ratio, and we're given the last term of the sequence. And we're asked how many different values are there in this sequence between 4 and 2,916. What this one is really going to show us is that we can take our general formula for a geometric sequence, which is t sub n equals a times r to the power of n minus 1. And if we know some of this information, we can figure out the rest of it, okay? So what do we know already? Well, we know our initial term is 4. We know our common ratio. We can double check it. From 4 to 12, how did I get there? I had to multiply by 3. Is that true from term 2 to term 3? 12 times 3 is 36? Yes. So my common ratio, R, is 3. And I know T sub n, the value of the last term, right? If this is the last term, then that term number is the answer that we're looking for. The number of terms in the sequence is this term number, okay? And its value is 2916. So here we go. We just sub in what we do know to find what we don't know, which at this point is the value of n, okay? Steps to solving this. Let's divide both sides by 4. So we get 2916 divided by 4, which is 729. 3 to the power of n minus 1. And then what I can do is simply write this left side. So I'm going to write 729 as a power of 3. Why do we do that? Well, this side is written as a power of 3. So if I can write 729 as a power of 3, then I'll be able to say that the exponent here on the power on the left side, 3 to the power of whatever, is going to be equal to the exponent here. All right? A couple ways to do this. You could just do 3 to the power of 3 in your calculator a few times, or you could try to do it in your head. I'm going to do it in the calculator, and it turns out that 729 is equal to 3 to the power of 6. 3 times itself 6 times. Now, since the bases are the same, comma, the exponents must be equal. There's no way around it. If 3 to the power of 6 equals 3 to the power of n minus 1, you can't get any other power to get the same value except for an exponent of 6. So we know here that 6 now equals n minus 1. And we took what looked like a challenging little expression here, thinking, oh, how are we going to do that? It's going to be like guess and check or whatever. It's not. We can just simply eliminate the base because they're the same. So the exponent must be the same. A little bit of algebra here. Add 1 to both sides. N equals 7. So there are 7 terms in this sequence. You're probably thinking, Mr. V, I could have done that in my calculator, just gone 4 times 3, got 12, times 3, 36, times 3 again, times 3 again, times 3 again, times 3 again. And I would have realized that after 7 factors of 3, I'd get 2916 in my calculator. Sure, but what are you going to do when, there's 100 terms or something like that? So go ahead, learn this, use it. Seatbelt use. Example 4. Seatbelt use became law in Canada in 1976. Since that time, the number of deaths due to motor vehicle collisions has decreased. From 1984 to 2003, the number of deaths decreased by about 8% every 5 years. So be careful with that. It's every 5 years, not every year, but you see that we have our common ratio given already. The number of deaths due to motor vehicle collisions in Canada in 1984 was approximately 4,100. What did they do there? They gave us our initial term. Our goal, determine a formula to predict the number of deaths for any 5th year. So any period of time where this common ratio would apply. Then we're going to write the number of deaths as a sequence. So determine a formula. let's see what we do know. We know that we're going to, it's a percent there. It's decreasing by 8%, which is a ratio question. So we're going to use the formula for a geometric sequence. Use the formula for a geometric sequence, which is t sub n equals a r to the power of n minus 1. What do we know? We know that in 1984, the first year, first period, there were 4,100 deaths in that 5-year period. Okay? Then, sorry, not in that 5-year period, in that year. There's 4,100 deaths in that year. It decreases by 8% every 5 years. So in the 5th year from this, it will be 8% less. Anyways, we know that the common ratio, and for this, it's kind of the same strategy that we've used in other things. If we're decreasing 8%, that means we're keeping 92%. We want to express that as a decimal. So r equals 0.92. And we can go from there. So here we go. So our new formula is the term value, t sub n, is equal to 4,100 times 0.92 to the power of n minus 1. There we go, for every 5th year. So now if you were to take a 5-year interval, you would just sub that in there, and you'd get the value. So this is A, done. Right. In B, write the number of deaths as a sequence for 5-year intervals. Well, let's just find each of those terms using our formula. Subbing in n equals 1. This whole piece reduces to 1, and we get 1 times 4,100 is 1. Second term, we have 4,100 times 0.92 to the power of 2 minus 1. So we're going to multiply 4,100 by 0.92 once. Okay. I'm just going to write down my next ones, and we'll do the calculations in a second. T sub 3, 4,100 times 0.92 to the power of 3 minus 1. T sub 4 equals 4,100 times 0.92 to the power of 4 minus 1. And we're supposed to do the first 5 terms, but I'm going to stop here. And here we go. First term, 4,100. Second term, 92% of 4,100 is 3,772. Third term, 92% of that is 3,470. Fourth term, 92% of the previous term is 3,193. And as a sequence, 4,100, 3,772, comma, 3,470, comma, 3,193, comma, and because it wants us to do 5, here's the 5th one, 2937. All right, a geometric, just quick review. A geometric sequence is a sequence in which the ratio of consecutive terms is constant. This ratio is called a common ratio, and you can use the general formula to find pieces that are missing. If you have some, you can find more. Okay? Your practice problems for lesson 6.5 come from page 392, numbers 1 through 9.